Good morning, Science 20s. Our lesson today is going to be on displacement in uniform motion and uniform accelerated motion. We will be using these two formulas in order to figure out these examples. They are located on page 2 of your science data booklet. Well, when I think of acceleration, I always think of acceleration lanes on the highway. So let's pretend in Medicine Hat we're going from the college onto the highway. There is always that shoulder lane, that secondary road where we take our initial speed, our initial velocity, and that's what we're going to enter this acceleration lane with. And we're going to speed up so that by the time we get on to the highway, we have a new final velocity. We are accelerating. So an acceleration lane must accommodate a vehicle from the time it enters with its initial velocity to the time it leaves with its final velocity. This is where it's supposed to adjust in order to speed up to get onto the highway. Now you'll notice that there's also acceleration lanes to get off a highway, and you might call those deceleration lanes, where you slow down so you can merge into slower traffic or you can merge to turn right or left. Got to clear that screen. So this is going to be our first formula. This equation is very useful for when we analyze accelerated motion because you do not have to start with a velocity time graph. So unlike what we've been using with graphing, I can do this by just having numbers. Again, in this formula, there should be no surprises by variables. Delta D with a vector arrow on top will be a displacement measured in meters. Therefore, it'll come with some sort of direction. We are going to take an initial velocity. We're going to add it to a final velocity. We're then going to divide that by 2. And we're going to multiply by the length of time it takes at a time interval. Again, we want to watch units. If time is in seconds, then my velocities should be in meters per second. Then, of course, my displacement will come out in meters. Again, we could do hours, kilometers per hour, and then this is going to come out in kilometers. Well, let's try a question. So, an acceleration lane example. A car enters the acceleration lane with an initial velocity of 65 kilometers per hour east. The car reaches a final velocity of 100 kilometers per hour east in just 4 seconds. Calculate the displacement of the car in meters. So, how far did it travel in this acceleration lane if we went from 65 to 100 kilometers per hour east in 4 seconds? How far did my car actually travel? How far should they make that acceleration lane? So let's make a list of variables down here on the side. We know we have an initial velocity of positive 65.0 kilometers per hour. Now, I'm calling it positive because that represents the east. We know we have a final velocity of positive 100 kilometers per hour. And again, it's positive to represent east. We know it took a time of 4 seconds to go from 65 to 100 kilometers per hour. And our job is to find what is the displacement. How far did our car travel? Now, they gave us a hint here. They said, convert from kilometers per hour to meters per second. Well, we should already know from the conversion lesson that in order to do this, it's actually quite easy. All you've got to do is divide the value by 3.6. Same thing, divide by 3.6 for the 100 kilometers per hour as well. And my number works out to be 18 positive 18.05 repeating meters per second, and 100 divided by 3.6 is 27.7 positive, and 7's repeating meters per second. Now, if I take a look at this, I have an initial and a final velocity. Therefore, I can use the first formula, the one we just looked at. So change in displacement equals initial velocity plus final velocity divided by 2 times our time interval. So when we go to substitute this in, we have a positive 18.05 repeating meters per second. We're going to add to that a positive 27.7 repeating meters per second. And we're going to divide that value by 2. Once we get that number, we're then going to multiply it by 4 seconds. So in my calculator, I'm going to take 18.0, and I'm going to just hit the 5 button a few times for repeating, plus 27.7, and again, hit a few sevens there. Enter, divide by 2, enter, times by 4. So I'm taking this number, adding it to this number, hitting enter, dividing it by 2, hitting enter, and then multiplying by 4 when we're all done. And my value when we are done is a positive 91.7 meters. Or we can say 91.7 meters east. Because remember, that positive represents east. So in 4 seconds, and it seems like not a long time, but in 4 seconds, when traveling from 65 kilometers per hour to 100 kilometers per hour, that vehicle traveled just under 92 meters. That's a pretty big deal. Now, if I take a look at this and I was giving marks, I would give 1 mark for converting to meters per second, 1 mark for the formula, 1 mark for substitution with units, 1 mark with answer with either a convention or a direction attached explicitly. Okay, so let's clear this. And let's do the second question. So, a baseball leaves a bat and travels straight up into the air, reaching its highest point at 15.9 meters. So we know its displacement. Because it's going up, we'll say it's a positive 15.9 meters. And it did that in a time of 1.8 seconds. We would like to determine the initial velocity of this example. Now, what is my final velocity? Well, I want you to think about this because it takes a second to, if you have never thought about this, it takes a second to figure this out. So if the ball goes straight up and it eventually hits 1.8 meters, the ball goes up, but it eventually stops and pauses for a brief second before it turns around and comes down again. So its final velocity in this trip is going to be 0 meters per second. Remember, it took 1.8 seconds to go from here to here. So my final speed when it gets to the top, the end of the time, is 0. So I can take my same formula I had before, but we get to simplify it. So I'm just writing down my original formula. And the nice thing about this is because my VF is 0, anything plus 0, 5 plus 0 is 5, 10 plus 0 is 10, happy face plus 0 is happy face. So I can just completely get rid of this guy because he's going to equal 0. Now, I want to move this formula around to solve for VI. So we have to ask ourselves, how are we going to do that? Well, let's move things over slowly. So currently we're multiplying by time. So we're going to divide by time, or it's currently on top. So I'm going to bring it to the bottom. There's my formula. I want to get VI by itself, so I'm currently dividing by 2, so I'll multiply by 2 on the other side, so we'll bring it from the bottom to the top. Two times change in displacement over change in time. Well, that's perfect. That allows us to substitute in. So I'm going to go up here to substitute in. So to find initial velocity, take 2 times my positive 15.9 meters. And remember to divide it by my time, which is 1.8 seconds. So I'm going to go 2 times 15.9, enter, divided by 1.8. And my value is a positive 17.7 meters per second. So my velocity is, my ball is traveling upwards at 17.7 meters per second, or if you want to say 17.7 meters per second up, you could do that as well. Again, when moving around the formula, just be careful, take your time, move one variable at a time. Remember, when we cross the equal sign, if it's on top, it's now on bottom. If it's on bottom, it's now on top. Our variables will switch floors. Okay, now we've used the first formula. The second formula, although it looks more complicated, it's actually a much simpler, more direct approach to solving these problems. The biggest thing I think you'll notice in this formula, though, is you'll notice that there is an acceleration value. In a lot of cases, when something is falling, so I'm standing on the edge of a diving board and I jump off or I fall off. I take a rock and I drop it off a cliff. Um, I jump up in the air and I'm going to fall back to Earth, right? All these are accelerations. Now, anything that deals with on Earth dropping an object, that's going to have something called acceleration due to gravity. And that number is always 9.81 meters per second squared. This number is on the bottom of your data booklet on page 2. This is a locked in value down here. And again, you can highlight it. And this is a constant. Anytime you're on Earth, when you drop an object, you have 9.81 meters per second square of gravity acting on that object downward. So in most formulas, you will see that number with a negative sign written in front of it. Let's try an example. So Jeffrey leaves the ground on a pogo stick with an initial velocity of 11.8 meters per second directed straight up. Okay, so that is his initial velocity. And since he's going straight up, it's a positive 11.8 meters per second. Determine the displacement. Okay, so we're trying to determine the displacement of Jeffrey after 0.8 seconds. So it doesn't take him long on this pogo stick. Now, there is a little note on this question. Remember, Jeffrey is under the influence of gravity. Because he's jumping, he's going to fall back down to the ground. And so gravity is having an effect on him. Therefore, we have to take a look at acceleration. And remember, on Earth, acceleration due to gravity is always negative 9.81 meters per second squared. I take a look, seconds, meters. I like the units. So we have a new formula for this. Our new formula is to find displacement, take the initial velocity times the time, add to it half the acceleration times the time. And this is what makes this formula tricky. You have to square the time on the second part of this formula. So what I would like to do is let's sub these values in. So positive 11.8 meters per second times 0.80 seconds plus Now we have a half. Again, our acceleration, because we're bouncing the pogo stick and he's going to fall back to Earth, is negative 9.81 meters per second squared. And the time is still 0.80 seconds. However, where this squared is part of the formula, so you don't do anything in your calculator, this value is squared, which means we will have to square the 0.8. So let's grab our calculator. 11.8 times 0.8, enter, is 9.44, plus, and I like to type a half in my calculator as 0.5 times negative 9.81 times 0.8, and then don't forget to square that value. So when I type this in my calculator, I get the displacement to be positive 6.3 meters. Which means the positive means that Jeffrey is traveling, and Jeffrey jumps pretty good if he goes 6.3 meters, leaving the ground on his pogo stick. Now, again, remember that is straight up, so this could also be 6.3 meters up. So he's getting quite a bit of height on his pogo stick. Probably not realistic unless it's some sort of circus pogo stick. Okay. So why don't we read this question and make a decision? Is acceleration a factor? If it is, we're going to use the second formula. If it's not a factor, we can go back and use the first formula. So this question is about a boy named Madison. Madison steps off the edge of a cliff. And so again, stepping off the edge, he's going to fall down. He's jumping into water. Gravity will play a factor in this question. Enters the water 5 meters below. So displacement is negative 5.0 meters because went down. If the initial velocity of Madison was 0, because again, started by standing on the cliff, so no initial velocity, I would like to determine how long. So my job is to find change in time. Again, because it's free fall, we are going to be talking about acceleration due to gravity, negative 9.81 meters per second squared. So meters per second, meters per second. I like the units. So my formula is going to be that big guy. Define displacement. Take the initial velocity times time. Add to it half acceleration times time squared. Now again, because my velocity initial is 0, 0 times anything is going to be 0. So these guys are going to cancel out. So I'm going to get rid of him right away. Again, my job is to get time by itself. So I'm going to move one thing at a time. So currently I have a 2 on the bottom. I'm dividing by 2. So I'm going to move it up to the top. So I'm going to have 2 times the displacement equals acceleration times time squared. Again, I'm currently multiplying by acceleration. So when I move it, I'm going to divide by acceleration. So I'm going to have change in time, and this is going to be squared, remember, equals 2 times the displacement over the acceleration. Well, there is a way to get rid of a squared. The opposite of squaring something is to do the square root. So when we are all done, my formula is going to be change in time equals 2 times the displacement over the acceleration square root. So let's sub some numbers in. 2 times negative 5.0 meters over negative 9.81 meters per second squared. And we have to square root this. So my time, 2 times negative 5, enter, divided by negative 9.81, enter. And then I'm going to take the square root of my answer, enter. And the amount of time it took for this was 1.0 seconds. Again, time is a scalar quantity, so there's no vector error or no direction required. Please practice with your calculator and make sure typing this in, you can get this sort of answer. Well, one of the reasons that we look at this is a lot of factors to do with driving. And my question I would ask if you were in class was, can you think of some factors that influence your reaction time? What is it that something that could slow down how fast you are able to react to a situation? This could be when you're driving, a ball or a little kid runs out into the traffic, how quick you can respond. This could be if you play knuckles with your friends, possibly. What are some factors that influence your reaction time? Okay, so one of the factors I always get is some sort of distraction. So distractions seem to be the number one, and seems to be that cell phones come up the most often. Maybe texting, which would be on your cell phone, comes up. Now in vans and vehicles, you can play movies, and depending, you might get distracted and try like leaning back to watch the video, which would be bad. Eating, because one of your hands or sometimes both of your hands might be now full and something happens and you can't react. Uh, Also possible could be fatigue. You're very tired. You're not kind of alert and responding as quickly anymore. Another thing might be you're on drugs. This could be on marijuana. This could be on things like caffeine or lack of caffeine. And another one that most students seem to be able to come up with is possibly alcohol. And I would think that we are all smart enough to know 0% alcohol before getting behind the wheel. Well, because you guys are at the right age for driving, I wanted to look at some stats on what are the crashing percentages for these distractions. So it is 23 times more likely to get into a crash because of text messaging or texting on a cell phone. It is 4 to 5 times more likely to get into a crash when talking on a cell phone. It is 3 times more likely to get into a crash when reading, and that could be an old fashioned map or looking at your phone to read a text message, or some people possibly even try to do more than one thing while they're driving to work. They read a little bit on the newspaper. It's 3 times more likely to get into a crash by applying makeup, looking in the mirror rather than on the road. It's 9 times more likely to get into a crash reaching for a moving object. So something is sliding on your dashboard. A purse might be sliding off the seat, or a Kleenex box might be moving around. So you reach for it, and now you're distracted again. It's 3 times more likely to get into a crash by dialing on a handheld device. And last but not least, it's 1.3 times more likely to get into a crash talking or listening on a handheld device. So when I look at these, it looks to me like one, two, three, four. Four of them are for sure cell phone, tablet related. And that's a huge concern because I think if anybody ever got into a big accident and it was their fault and something severely either happened to you or somebody in your vehicle or maybe somebody you don't even know in a neighboring vehicle, you would probably have a really hard time trying to lose those feelings if you did something that caused some permanent damage.